The second session, we will try to investigate a bit more deeply some issues that were already raised in the introductory session. So we're going to have a presentation by Lynne Schofield, who is Associate Professor of Statistics at Swarthmore College. And she will present this MICI model that should be able to solve some of the problems that were raised. But you need item-level data for that, which we have. And then we're going to have a presentation by Sergio Urzua, who is Associate Professor of Economics at the University of Maryland. Mattia said that IRT is nothing but a class of factor models, so he made this analogy. And so Sergio will talk about how economists have used factor models, and we'll talk about his research. So Lynne, the floor is yours.
Thank you very much. Thank you so much for having me. So I have to admit that when I got this invitation, I wasn't sure if I was being asked as a psychometrician or an economist. My PhD is actually in statistics and public policy, and so I had both a psychometrician and a labor economist as advisors. I also have a father who's an economist and a mother who's a psychologist. So I don't know what's genetic. I don't know what's nurture. I have no idea. And if Matthias's comment is correct, then maybe this explains my life in some sense about the bridge between economists and psychologists, but there you are. The motivation here has sort of already been outlined pretty well. I'm going to focus pretty exclusively on the case where we are thinking of the latent variable as the independent variable in the analysis, right? And so lots of individuals in the social sciences, I've given just sort of two kind of seminal papers here as examples of cases where latent variable or latent variables have been used to predict some other outcome of interest. So Neal and Johnson, all the way back in '96, used the Armed Forces Qualifying Test, which is a test used in the US to decide essentially whether or not you can join the military and then what job you might have in the military to understand the black-white wage gap in the US. And Heckman and his colleagues, and in fact many of his colleagues, have used not just cognitive abilities, but also several non-cognitive traits, so personality traits, motivation, conscientiousness, all sorts of other aspects of that, to really understand lots of later key to lots of later life outcomes, not just in the labor market, but in health and educational decisions and others. And so, as Jesse pointed out, right, a pretty typical model to study these effects is a regression model, right? Although there's nothing that forces us to have this be a linear regression, right? Any kind of nonlinear regression, logit, probit, Poisson regression even can be used, where we're going to have some outcome of interest. So if we're looking at Neal and Johnson's paper, that might be log wages. We're going to have some set of latent variables. So far, everyone's been kind of just talking about that as being one latent variable, but we're going to look at some examples later about cases where we might have multiple latent variables that all might be correlated with one another and their individual effects and their joint effects on what's happening. And then some additional covariates, which I'm going to use Z throughout this talk to talk about. So that could be race, years of labor force experience, other kinds of things along the way. So what economists do is they write this model down, and they say, this is the model that I want to estimate. But as Jesse pointed out, while most of them want to estimate equation 1, what they really only have is equation 2, which is some estimated amount of the latent variable that they have, some theta hat. And has been discussed in lots of cases here, right? If we ignore the measurement error in that variable on the right-hand side, we're going to come up with lots of biased results. Jesse said that economists care a lot about, or have looked a lot at cases where that's a classical measurement error. And so when that's true, beta 1 is going to have sort of a well-known attenuation bias if you have that classical measurement error. And beta 2, its bias is actually going to be dependent on the relationships between and the correlations among Z, theta, and Y itself. So in fact, we can sign it, but we have to only sign it if we understand the relationships that exist among those variables. When we don't have classical measurement error, the size and the bias of this depends on lots of various other things. And so understanding each one of those cases is going to be more complicated. So if we imagined a world in which theta is observed and known and doesn't have measurement error, then our likelihood's pretty simple, right? It's just y given theta, z, and beta. And that's a pretty easily solvable problem. We can either use maximum likelihood estimates to come up with estimates of beta, and maximum likelihood estimates have lots of properties that we like that make us pretty happy. But when theta, or we can be Bayesian and we can put priors on beta and come up with posterior means, which also have lots of nice properties that we enjoy. When theta is unobserved, though, then, and then what we've observed is not just these outcomes of interest, but we've also observed some either proxy test score or what I'm going to use as a set of item responses, x, then our likelihood becomes a little more complicated. Now it's this joint distribution of y and x together, given beta and z. And since we don't observe theta, it's kind of not in there. But, in fact, we can recognize that essentially that joint distribution is really just a marginal distribution of a more general model where we've integrated theta out. And so if we unintegrate theta out, if you will, if we throw that in there, and then we use the law of total probability, what we end up with is this model that includes some model of y given all of these variables, x, theta, z, and beta, some aspect of a model that has x given theta, z, and beta, and then another model, which we've been calling this conditioning model of theta given z and beta. So this informs a form of what we've named the mixed effect structural equations model. Now I'm going to simplify this a little with three pretty relatively simple assumptions that we've got. So first, I'm going to assume that y depends only on theta and z. So once I know theta, knowing the item responses doesn't give me additional information about y. Second, I'm going to assume that theta is conditional on beta given z, right? Once I know z, the effect of z on y doesn't really tell me much more about theta. And I'm going to assume that the item responses are independent of any of those background variables, right? So all of these assumptions kind of come from most of good measurement practice, right? If we have a good, well-designed test, this should be true. So if I do that, then I'm going to end up with, in hierarchical form, this MICI model. This model actually was sort of discovered, if you will, or sort of explained by Richardson and Gilkes, who are two people who work in epidemiology. And they lay this model out in some sense as the highest level being the structural model, then a measurement model of some kind, with this conditioning model as well. So what I'd like to do, sort of for the remainder of my time, is go through each of these sub-models in a little bit more detail, and then I have two examples of the MICI model in practice. Okay, so let's start with the measurement model, which Mateus laid out pretty well for us already, so I won't spend lots of time on this, right? But we suggest that whatever model was used to construct and score the test is probably the model you ought to use as the measurement model itself. And so what makes this nice is that there's nothing that forces a particular IRT model within there. And in fact, we found that misspecification of that IRT model, so if you use the 2PL instead of the 3PL, if your item characteristics parameters are slightly off, in fact, that doesn't seem to affect the betas too drastically. So there's some simulation work that's been done on that. We've already seen this 3PL model laid out. That's really for binary items when we have some right-wrong answer within there. And then we've got these graded response models that we can use for Likert scale surveys or other ordinal items along the way. So I put this up here because these are going to be the two models we're going to use in some of the examples that we see later. One point I want to make, though, which I think hasn't been as fully made maybe in some of the other talks as we might want to think about, is that IRT models not only give us an estimate of theta itself, but they actually give us an estimate of that standard error of theta. And we can find that pretty easily asymptotically by just taking the inverse of the square root of the Fisher information, which isn't too hard to calculate. However, I think it's pretty important to note that that measurement error is not even across all individuals within the distribution. Right, so here's just sort of a typical 3PL model. The kind of top line has 5 items all the way down to 50 items. And what we'll see is that the standard error varies for people along the various parts of the distribution. And it tends to be largest for those in the tails. So it tends to be largest for those who are particularly high ability or particularly low ability. And it tends to be closest to wherever the test is, which tends to be somewhere in the middle of the distribution. We're also going to see that that standard error goes to 0 as the number of items, j, goes to infinity. So essentially, a lot of this work that we've been talking about, right, about this measurement error, if we have a really, really, really long test, it may be that plopping theta hat into your regression model really is okay because that measurement error is particularly small. Where this is going to be particularly problematic are in cases when the number of items on your test or your survey is small. And so how small is too small? How big is too big? It's a universal question we all have, right? And finally, unfortunately, the standard error is also unknown for all individuals because it's dependent on theta itself. And so there's been some work at looking at, well, if we can calculate the standard error, can we use some sort of form when we're thinking of our thetas as independent variables about sort of adjusting in some sense independently. But Lockwood and McCaffrey showed that if you estimate the standard error using theta hat, you end up with bias just the same. So that's not really a solution that we can use. Okay, so now on to this conditioning model. I'm going to spend a little bit of time talking about this. So most often, this is assumed to be somehow multivariately normally distributed, especially depending on the number of thetas that you have within your model. We are allowing for possible differences in the subgroups within the distribution of theta so that people in different groups can have different theta distributions. And both myself and Amy Drescher, who was at ETS, have shown that this misspecification is relatively robust within. So it turns out that various subgroups are probably not normally distributed, right? So people who are particularly high ability or of a certain race or a certain gender or a certain socioeconomic status might not have, that particular subgroup might not be normally distributed. But assuming normality doesn't turn out to matter too much when we're thinking about the effect of theta and the effect of some of these other variables on this outcome of interest. The real question, though, where bias can really occur is in the question of what variables need to be included within this model. And so we've already discussed this a little bit, so I want to kind of add my perspective on this. So of course, many large-scale assessments, NAEP, PISA, others, follow Miss Levy, and they condition on this kitchen sink idea of what's going on to avoid bias in any population statistics. What my colleagues and I have shown, though, is that we think there actually should be more of what we call a Goldilocks result to the conditioning model when you're thinking about theta as an independent variable. And by Goldilocks, I mean that it shouldn't be too big, it shouldn't be too small, it should be just right. And so what we suggest, and what that law of total probability in some sense tells us, right, we have to follow it, it's a law, yes, is that theta should be conditioned on all the covariates that are in the structural equation, but it should not be conditioned on y or any other variable associated with y conditional on theta that's not already in the structural equation. So Jesse mentioned that he didn't really understand what that congeniality concept means, so I'm going to try and give you a pretty simple example of what I mean by the congeniality that's needed if you're going to include y in your conditioning model, and then have a structural model in which theta is in fact an independent variable. Okay, so let's assume that the conditioning model on theta, which is often placed there by the survey institution in some sense, we're going to choose a pretty simple case. We're going to choose the case where we've got some linear regression in which theta is conditioned on both y, the outcome of interest, and those background variables. Okay, this is a pretty simple model in this case. So by the law of total probability, once I have assumed a certain model of theta given y and z, that forces a particular model for y given theta and z, right? That's just Bayes' rule, essentially, yes? So if I also make the assumption that that marginal distribution of y given z is also just a linear regression that we have here, then what I can see is that I can actually calculate out, based on those two models, what the model of y given z and theta has to be. It's going to continue to also be a linear regression, and the estimates, or essentially the coefficients in front of theta and z, are going to be dependent on the coefficients that were used in the conditioning model, as well as the variance that was in both the conditioning model and that marginal distribution. So if you're the secondary user, or you're kind of coming along and you're using a MICI model like what I suggest, as long as you believe that the right structural model is this model that has these alphas and these in front of theta and z, then that conditioning model will not produce unbiased estimates. You're fine. That's going to work great. But if you want to estimate a model in which maybe you're going to throw theta in as a quadratic function of y or something else, any other model other than 12, equation 12, which I've written there, is going to produce some kind of bias. So you're going to have this non-congeniality. It's not going to match the conditioning model. And I'm not really sure what to do with a model that has y given theta and z in one direction at the same time that it has theta given y and z in another direction. Probabilistically, that just doesn't work out the way that I want it to. So I ran a few simulations to give some examples of exactly how to do this. And again, this is in a very simple case that I did. So in these simulations, I should say misspecification, I'm going to show in these simulations that misspecification of which covariates are in the model will produce bias, but the amount of bias really is a big part of the question that we're having, right? So the amount of bias is going to be based on the number of items on the test, essentially how much measurement error there is in our value of theta, and the strength of the correlations between y, z, and theta themselves. So let me show you a pretty simple set of simulations to give you an example of what I mean. So I ran a model in which the structural model that I have is an outcome of interest. It's dependent on theta, and it's also dependent on probably the simplest background variable you could have, a binary variable that indicates whether or not an individual is in a reference group or a focal group. Okay. So in the first case, I used what I'm calling the just right conditioning model. Okay, so I included z, but I did not include y in that case. And what we see, and I did it for 4 cases. I did a 6-item where the difference in the means between the focal group and the reference group is pretty large. And then I did it for a 6-item case where the difference is much smaller. That's my way of sort of looking at the correlation that exists between z and theta itself, right? So how much do we need z in that conditioning model versus not? And then I did it for a much longer test, for a 50-item test. Okay, and you'll see when I use the just right conditioning model, we're fine. Things work out the way we expect them to. Everything's hunky-dory. I essentially then did a case where I have the too small conditioning model, right? Here, I'm not including z, so in this case, I don't have any other covariates in my model, so nothing is really in the conditioning model. I just assumed theta was normally distributed with a mean of 0 and a standard deviation of 1, and we see that we end up with bias, but what we see is that that bias is very much dependent on the length of the test. So let's think about why that might be. One way you can think about this conditioning model is that in some sense, it's really just a prior on theta. And that when we combine the conditioning model and the measurement model together, what we're getting is a posterior distribution of theta based on the data that we have and the prior that we have. Any good Bayesian is going to tell you that the more data you have, the less the prior affects the posterior distribution. So when I have 50 pieces of information, when I have a 50-item test, I have lots of information. The prior doesn't matter as much, right? So whether or not it's misspecified doesn't really matter quite as much along the way. When I have a 6-item test, I have much less information. I'm in much more trouble, and there I really need the prior to be sort of appropriately assessed. Now let's look at what happens when I have a too large conditioning model. This is where I've included y in the conditioning model itself, and we can see that both for beta 1, which is the estimate of theta on y, and for beta 2, which is the estimate of z, that reference focal point, I end up with huge bias in the case where I have only a 6-item test. But again, in the 50-item test, the bias is not as great. And what we also see is that when the correlation between z and theta is much larger, I end up with even more bias in beta 2 and that effect of z on y than when that correlation between the two is less important. Why would that be? Well, it turns out that if z is completely independent of theta, that it doesn't really matter whether or not you have it in the conditioning model, even if it's in the structural model, right? Because if z is completely independent of theta, let's go all the way back here if we can to, Is this slower than mine? Here we go. Right? If z is completely independent of theta, then equation 8, that f of theta given z, well, that's just the same thing as f of theta, if those two things are completely independent. So the less the relationship between theta and z, the less it matters whether or not z is actually in the conditioning model. The final thing I did was then I also included a variable, what I'm calling v, which is correlated with y, but is not in the structural equation. And when I include that in the conditioning model, I don't include y, but I include this variable v that's correlated with y, but not in the structural equation, I still get bias, although it's not as great as the bias as including y itself. And finally, if I include some variable w that's correlated with theta, but has no information about y whatsoever, I don't end up with any bias at all. And so I sort of still have this just right conditioning model. So the kitchen sink approach, at least in the case when you've got an independent variable, turns out to be particularly problematic if the kitchen sink includes the outcome of interest, or it includes some variable that's correlated with the outcome of interest, but not necessarily any other variables. So it really is okay for us to say include some variable that's correlated with theta. In fact, it might give us better estimates if we include variables that are correlated with theta but are not correlated with the outcome of interest. Okay, then finally, our sort of third submodel of the MICI model is the structural model, right? So this is, of course, your equation of primary interest. We're kind of, in some sense, treating theta as a random variable in a mixed effects regression, and so we're allowing theta to vary, and we're allowing it to vary across that posterior distribution that we end up with based on the conditioning model and the IRT model along the way. And it's going to be able to be pretty accommodating to all sorts of different areas. Any kind of generalized linear model we've checked seems to work. Okay, so I want to give two examples of using MICI in action and compare the results that we get when we use a MICI model with what we get if we just use an OLS model. So the first example comes from the idea of retention in the STEM, which is the science, technology, engineering, and mathematics disciplines. At least in the US, we see that there are differences in the number of whites versus the number of blacks and Hispanic students who persist, by which I mean that they declare a STEM major at some point during their college career and then graduate with it. There are lots of people who declare or sort of intend a major in STEM and then they drop it at some point. And it seems as though whites persist more than blacks and Hispanics, and that men persist more than women. There are a host of studies that are trying to understand the reasons that underrepresented minorities and women leave STEM in larger rates than do men and whites. And many of those include latent variables across the spectrum of kinds of latent variables. So some of them include things like academic achievement. Mostly it's math proficiency. But lots of them also include all sorts of other psychological variables along the way. So those include the math and science identity that the student has about themselves, their interest in STEM in general, their ideas about sort of future time perspective, what they're going to do with this, how is this going to help them in some way get a job or other areas, their sense of community within the major, the goals they have for their for what they're going to do, and then all sorts of different aspects of their personality traits along the way. So we're going to model STEM retention using a binary measure of STEM persistence. We're going to have a vector of latent variables, and then we're going to also include a bunch of these demographic variables to try to understand these gaps. So I use the National Longitudinal Survey of Youth. I use the 1997. This is a particularly useful survey in the sense that we have longitudinal data. So yearly the students are asked what their major is, and so we can actually track when they have STEM majors and when they're dropping them or when they're not dropping them. So I declared YI a stayer, which is someone who persisted in STEM. That's equal to 1, versus a leaver, someone who declared a STEM major but didn't persist to graduation. I've included race as just a binary 1 when you're an underrepresented minority or not. There are reasons to separate out the various racial categories, but for this case, we just put them all together. And then we have gender indicating a female gender or not. We have 6 latent variables. So the first is the PIAAC, which is a measure of cognitive proficiency in mathematics. Students get somewhere up to 100 items on this test, although most are getting about 10 to 20, because they tend to use a floor-ceiling method as their way of scoring this test. And so it's dependent on how many items they answer correctly and how long they answer them and so on. And then I've also used the TIPI, which is the 10-item personality inventory, which measures the big 5 personality traits of extroversion, agreeableness, conscientiousness, emotional stability, and openness. This is a 10-item survey that's measuring 5 different constructs. So what that tells you is that there are 2 items per construct. So this is kind of a nice, useful example of when it is that we're going to actually need to account for this measurement error versus not, how big a difference this is going to be along the way. So just to give you some idea, within the National Longitudinal Survey of Youth, women do not persist at the same rates as men do, and underrepresented minorities persist at lower rates than non-underrepresented minorities. And if we look at these scores across the PIAAC and the TIPI, we'll see that women and men at this stage have about similar kinds of math proficiency, but underrepresented minorities have lower scores on their math proficiency than non-underrepresented minorities. On the personality tests, these tend to be relatively similar, although you will see that in the NLSY, as in what's sort of well known within psychology, women tend to be more agreeable with men. You guys can decide what you think about that. And that women tend to be slightly less emotionally stable. You can also decide what you think about that. And so what we have here are essentially 4 logistic regressions. The first is a baseline in which we did not include any of the latent variables at all. Then we have a logistic regression where we've included the PIAAC, one where we've included the TIPI only, and one where we've included both. And we ran them under 2 specifications. So the case where it says adjusted for ME, no, means that we just did an OLS regression there. So we didn't adjust at all for measurement error in that case. In the case where we have adjusted for ME, yes, we did use the MICI model as our way of adjusting. And so what you'll notice is that you do get different results when you adjust for the MICI versus not adjust for the MICI, but that the differences are far greater for the case where we've got the TIPI than they are for the PIAAC, right? Because we've got 2 items on this. And so in fact, when we when we don't adjust for measurement error, it looks like even after controlling for personality scores and for math achievement, in fact, that women are still persisting at lower rates than men. But when we adjust for measurement error, we see that that becomes non-statistically significant. So we get particularly different results with the same model, whether or not we adjust for measurement error or not. And we also see that we're greatly underestimating the effect of these personality traits in particular, and slightly underestimating the effect of PIAAC on persistence in STEM. So our second example comes from sort of a lot of work currently happening in economics right now is trying to understand the intergenerational transference of human capital. So Raj Chetty at Harvard and some of his colleagues have been looking at geographic places and how that might affect this intergenerational transference of human capital. And they've been mainly using income as their way of doing that work. And we decided, well, what if instead we used these measures of human capital that we have along the way? And we tried to measure a mother's human capital with a particular test score, and then her children's measurement error using a test score as well. So ideally, what we want is to measure sort of theta at the child level as dependent on a random intercept model where we're going to have a random intercept for mother. So P is the mother in this case, since moms can have more than one kid. And have the child's human capital will be dependent on the mother's human capital. So we've adjusted the MICI model to do this. Now in this case, we actually don't have a conditioning model because we're going to split the data into 3 different groups. We're going to split it by race as blacks, whites, and Hispanics. And we're not including any other covariates, so we don't need any other covariates essentially in our conditioning model in this case. We're going to, again, use the National Longitudinal Survey of Youth, only this time we're going to use the 1979 wave, because there what we have is not just the mother's information and item-level data at the mother, but we also know information about all of her children, and we have item-level data on the PIAAC for that. So for the mother's human capital, we're using the AFQT again. This is an 104-item subset of the ASVAB test. One could argue that since the AFQT is in fact 4 subtests put together, that maybe the unidimensionality assumption is poor here, but we're going to go with it anyway. And then we also have the PIAAC score for each of the children here. And so we're going to report the impact of a 1 standard deviation increase in the mother's AFQT score on the number of standard deviations her child's PIAAC score for both OLS and MICI. So here what we see is that when we do not adjust for measurement error, we're actually overestimating the effect of mom on her children. This is good news for my kids. What we also see is, in fact, that we get differences in the amount of human capital transference, or in the correlation, if you will, between races. So, some kind of final observations. Measurement error inherent in latent variables is incredibly important to model when we're using the latent variables as an independent variable in a regression or any kind of generalized linear model. We're going to have bias if we don't model that measurement error, both in the effect of the latent variable itself on the outcome of interest, but also in any other covariate that is correlated with the latent variable that's also in the structural model. That bias is going to increase for shorter tests and shorter surveys. So if you want less bias, what you have to do is not increase the number of individuals in your study, but you have to actually increase the number of items on the test. One way to do this is this MICI model, but of course, what that means is that we then want lots of individuals and we want lots of items. So this is an incredibly data-hungry model, and I'm going to admit things don't run in the 2 seconds that an OLS model runs and say R or stata along the way. But the results that we get are substantially different than OLS. In the STEM retention gap, we find that OLS was substantially underestimating the effect of the latent variables, and especially these personality traits, because J was so small in that case. The racial gaps became insignificant after controlling for both math proficiency and for its measurement error. And once we controlled for measurement error, the results suggested that comparably skilled and comparably traded men and women were actually equally likely to remain in STEM. And at least among the intergenerational transference of human capital, here we're actually saying that OLS was substantially overstating the degree of the correlation, especially for Hispanics and African Americans. The correlation is strongest for whites. One could argue that might make sense when you think about kind of racial inequities that have existed in the United States, and the academic progress that's been made over the last 30 years or so by Hispanics and African Americans within the United States. But that the correlation that we find is pretty similar to those found in Solon and Chetty and his co-authors for whites, but is substantially lower for blacks and Hispanics. And so we may have to think more carefully when we're doing this kind of work about separating out by race. So thank you very much.
Thank you. Now we have a talk by Sergio Urzua on the use of factor models in economics and application to education.
Great. Like 3 a.m. in the morning. So, all right, so first of all, thank you for the invitation. It's great to be here at the OECD to talk about factor models in economics. Very exciting. So let me get into what economics, how economists have been using factor models with something that, you know, if you ever tried economics in college, you probably saw something like this. So it's an agent maximizing utility, trying to maximize select consumption and leisure, right, and subject to some constraints, right? So this is our starting point. Why we want to get into factor models? Well, it's actually because we are trying to understand how people make decisions, right? So we have individuals maximizing utility over time. There is a discount factor, right? There is a parameter that defines your utility function, the curvature of your utility function. And then you have these constraints. They could be static or dynamics, but basically they tell you, the way you produce labor income might depend on some structural parameters. The way you accumulate human capital, it will depend on some parameters. And then you also have these initial conditions, right? You have initial conditions. You're bringing your initial conditions to whatever decision you're trying to make. How do we link this to factor models? Well, there are a lot of structural parameters here we'd love to know. In principle, you can think of preferences, human capital productivity, labor market productivity, and even the initial conditions as a function of these unobserved components, these latent factors, right? They could be skills, they could be endowments, but these are unobserved. The agent knows them, they act based on this, but the econometrician, the economist, is trying to figure out how those factors are affecting the way you make decisions. And this is connected to what Lynne was saying before. We need to use information to identify these factors, and we have spent a lot of time trying to get good data, right? Economic research has been using all sorts of sources of information to get different candidates for these unobserved components theta. It could be cognitive ability, could be socio-emotional ability, it could be time preferences, could be, again, risk aversion and so on, but those are unobserved components. So do we have the data to say something about these unobserved components? And why are these, this is, and there's tons of papers looking at this from this perspective, but to be fair, we are not there yet. We are still trying to figure out how to connect the way you evaluate the future, your discount factor, or how risky or risk lover or risk neutral you are in terms of your decisions, map them in those decisions into these structural parameters, and factor models can help us to do that. So let me show you an example of something we use a lot in economics. This is a simple Roy model. You have two states, two regimes, treatment and control, right? This is something we do a lot in economics. Then there's a decision rule. The individuals are making decisions based on some sort of information they have. The econometrician observes X's and Z's, but of course the error terms are unobserved, right? But the agents might have information on the error terms. The agents might have more information than the econometrician. And in principle, think about this decision process as something like, well, there's an unobserved component, this theta, which is linking your decisions with your outcomes. And so potentially your treatment effects will be affected by those unobserved components, right? So if you're looking at the impact of a specific training program, if you're looking at the impact of any sort of social safety nets, access to education, access to college, and so on, you might expect people are being rational, they're comparing these outcomes, but they are making decisions based on things that the econometrician doesn't observe. And that's the link between how the agent is maximizing utility, trying to figure out how to consume, how to decide, this setup, and the factor models, right? So that's the idea. So I will show you at the end a few examples if I have time. But something we have been doing a lot in economics is trying to figure out the impact of schooling, of years of education on wages, right? Labor market outcomes. So the way you want to think about this in the context of what I just showed you, well, you have this unobserved component. It might have two dimensions, say cognitive and non-cognitive or socio-emotional. Those unobserved dimensions are known to the agents to some extent. They are then affecting the way the agents is maximizing utility, deciding how many years of education they want to attain. And it might be affecting these two unobserved components, might also be affecting directly your labor market productivity. So at the end, you have this structural model in which you have these latent factors being linked to test scores, right? And that's the way we're going to be identifying this. But those factor models are being used to identify the impact of abilities on education and then education on earnings or wages, taking into account the fact that, again, these unobserved factors should be affecting everything, right? Your skilling decisions and your labor market outcomes, right? So factor models can be integrated into this economic setting. What else? That's sort of, I mean, it has a bit of dynamic, but we can do better than that, right? So when it comes to, you know, policy making, what you want to have in mind is, well, we are collecting better data. We have longitudinal information. We are linking administrative data with survey data. So those, that new setup, right, that new environment allow us to do more. So think about this as a human development at each stage. So you have childhood, they have teenage years, adulthood, and old age. And then in each of these periods, you have inputs and outputs. Again, this is sort of the economic perspective on this issue. So inputs might include your endowments, could be your genes, environment early on. Then you interact with the, you know, human care, the healthcare system, childcare system, school system, your family, of course, is important. And at the end of that period, you're going to have some outputs. Those are going to be cognitive development, non-cognitive development, physical and mental health, for example. And that happens at every single stage. And then, of course, they are connected. The outputs of one stage are going to be the inputs of the next step, of the next stage. So you want to have dynamics, right? You want to have this. Whatever is affecting your decisions in this period, they will probably be affecting your decisions in the next period. But more importantly, if you're going to be focused, if you want to focus on public policies, well, you better understand how these factors are related to, you know, interventions and different policy decisions. So that's the next step, right? So if you look at now this figure, you're wondering, well, how do we incorporate dynamics? So factors could be dynamic. The factor models can allow for dynamics. So let me show you one example of this. And this is something, you know, people have been doing for a while, and it's actually quite common in macroeconomics, but people now in microeconomics are using it more and more. But now, so think about this as, you know, you have a latent factor, could be a vector in period T. There are some investments that might help to boost this factor. That's going to be IT. So you can think of the factor in period T, or this unobserved skill in period T, as a function of your skill levels in T minus 1, investments between T minus 1 and T, plus some measurement error, a shock. And investments themselves could be a function of these unobserved components. And then you have initial conditions. So we know now how to estimate these models, and this is just an example of how important these factors are. Well, this is data we did actually with a project with the OECD back in 2013, where we look at data from South Korea. We have multiple rounds of test scores. So we were able to identify the distribution of cognitive and non-cognitive test factors at different ages, and you see there just a picture to see how they change over time, and they do change over time. Right. Of course, you need a lot of data to do this, and I will discuss this in what follows. But in principle, you see two things. Factors can evolve. These latent factors can evolve. Two, they are not normally distributed. It's something that Lynne mentioned before. So we want to take that into account. And also, and this is sort of new stuff in economics, I will say, there's something also interesting when it comes to understanding inequality. And this is, I find this super exciting. I think connecting what we have learned from these factor models into income inequalities is going to be the next step in the profession. So what's going on here? So think about your earnings, right? So you're bringing your earnings, you're bringing your human capital, but what is human capital? So you have initial pre-labor market conditions plus the skills, and they combine somehow to produce what you do in your job or your tasks, right? And then you look at your earnings, and your earnings in this context will be a combination of your pre-labor market conditions, your skills, right, that can evolve over time, plus whatever firms' characteristics are important for deciding your labor market productivity, and then the match between you and your firm, right? So you have these three components. The first one It's what has been labeled in the literature these efforts, right, and circumstances, right? This is something that the individuals bring into the firm. Then the first components, right, and then the product of this the matching between these two dimensions. So at the end, what we do when we compute, for example, a Gini coefficient in period T, well, we combine firms and individuals. That's what we observe, right? But if you think of wages as the combination of the three components, well, the evolution of these latent skills, which probably define your pre-labor market conditions, your endowments, your skills, and your tasks, will be shaping the income distribution. That's, the next step. So where are they coming from? How in economics, how these factors can be identified? And this is something that has been discussed before, so I don't want to spend much time on this. But basically, we have a measurement system. We can somehow control for family background characteristics, and then we have a factor affecting this test score and measurement error, right? That's the logic. But beyond just incorporating this measurement system in our empirical strategies, a key question is, how to identify it. And economics identification is super important. We want to have flexible functional forms. We want to try to avoid or at least test for some structural assumptions. So let me show you one simple strategy and why these test scores the number of test scores is important for identification purposes. Suppose you have 3 test scores and you have one factor. So suppose this is data from, say, the analyst Y79. You have information on battery of different items. And so you have item 1, 2, and 3, and you write down these 3 items as a function of this unobserved component theta, right? These items basically share this component plus shocks, measurement error, these epsilons. Well, of course, in the right-hand side of those 3 equations, you don't observe theta, you don't observe the epsilons. The agent has information on theta, that's assumption, but you do observe the left-hand side. So you can compute the covariance between T1 and T2, that's data. Covariance between T2 and T3, and you can do the same thing with T1, T2, and T1, T3. Take the ratio. You do observe the left-hand side of those 2 equations. And after one normalization, you can recover the alphas without knowing the thetas, right? At this point, we basically are not imposing any assumption on the distribution of theta. It could be anything, right? Next step. Well, you take the alphas, you go back to the equations, you write it down this way, and it turns out there is a theorem back in 1967. Kotlarski shows that in systems of this form, you can non-parametrically identify the distribution of the unobserved components, epsilon t and epsilon t2, and the non-parametric identification of the distribution of theta is also secure. What this is telling us, now with this theorem, so we need at least 3 test scores, right, and 1 normalization, you can non-parametrically identify the distribution of the latent factor. That's cool, because then, if I know that, I go to my likelihood function, as Lynne was showing before, and now the last term there, that f of theta, I can be flexible. I don't need to impose normality, right? And now, not only that, we can test for whether normality will be rejected in our data, right? So identification is very important, and there are different strategies, empirical strategies to accommodate that identification strategy. One would be maximal likelihood, you could be Bayesian too, but from the economic perspective, what we really like about this setup is that we can try different functional forms for the factor. All right, so I have like 10 minutes, right? Perfect. So I have 3 applications. I will probably discuss 2, and if I have time, I'm gonna tell you a little bit about these dynamic treatment effects. So let me show you, first of all, the application on abilities, straight application for abilities. A paper we published a few years ago with Prada, and so the idea is the following. So we know abilities are multidimensional. Right? We have been talking about cognitive and socio-emotional, but in principle, within those 2 categories, you have multiple dimensions. So what about mechanical ability? Right, mechanical ability is something like dexterity, is something that, as kids, you see kids improving and so on. How important is mechanical ability for understanding labor market outcomes, for example, or schooling decisions? Of course, these skills are going to be unobserved. We have test scores, right? The kids run different test scores to measure their mechanical ability. But it turns out in principle, you don't want to really use those test scores because, again, they could be influenced by, family background characteristics, measurement error, and in principle, latent factors. So we're going to incorporate what we just discussed in a setup in which we have longitudinal information on decisions and labor market outcomes again. And what we show in this paper is that once you take into account you use this factor model, you find the mechanical ability will actually reduce your probability of going to college, which is sort of odd, right? Is, what we think of skills as, things that will improve your chances of going to college. It turns out mechanical ability doesn't do that. But why? Well, it turns out mechanical ability has a huge return on the labor market, but for those individuals not going to college, which is sort of, once you think about it, it sort of makes sense, right? You don't have to really have, cognitive ability, high levels of cognitive ability, or non-cognitive ability to do well. Maybe you have people with different bundles of skills, and so this could be an opportunity for those fellows not lucky enough to have high levels of the other two, right, by high levels of this mechanical ability to do well. So that's sort of what we do in this paper. So think about this as mechanical ability being correlated with cognitive. So actually, we show the correlation is pretty big. There's social-emotional skills as well. The three components of schooling affect the schooling, and then you have the effect of on wages. So where's the data coming from? NLSY 79, right? I'm not going to get this since Lynne already mentioned it, but just let me point out that the ASVABs in the NLSY 79 have this mechanical comprehension section. And economists has been, I have to admit, we have not paid enough attention to these dimensions. So basically the ability to solve simple mechanical problems and understand the basic mechanical principles. So we're going to be using a ROI setup, 3 correlated factors, college and earnings, MCMC. We're going to be estimating using MCMC. That's the structure. So you see how now we have a ROI model, college versus high school, earnings after college, and then we observe a decision rule. Of course, error terms are correlated. How are they correlated? They have these 3 factors affecting this the error structure. And they are going to be independent from these shocks, but the factors are going to be correlated. How do we estimate this? Remember I told you about this flexible functional forms, mixture of normals. So we don't have to impose normality, right? Once we have secure identification, we can go to flexible functional forms. We are going to be using mixture of normals. Let me show you some results. So first of all, how noisy these test scores are. So this is a simple ANOVA decomposition. So we're decomposing the variance of these test scores in 3 components: observables, unobservables, the latent factors, and the error term. What we find is that, first of all, a lot of heterogeneity across different measures. 2, the factors actually explain a large fraction of the variance. 3, but you got to be careful because these test scores are really noisy. So if you want to just plug these test scores on the right-hand side of a regression model, you're going to be facing biases. So you got to be careful with this. The factor model allows you to control for that. This is the distribution of cognitive and mechanical ability, highly correlated, which is actually interesting, given that the effect on schooling decisions and earnings are different, right? So you are looking at, if you're moving someone from the bottom to the top of the cognitive distribution, the correlation with the mechanical ability is positive, so you're going to be moving people from the bottom to the top of the mechanical distribution as well, but the impacts are differential. So this is cognitive ability. Let me go into mechanical because that's the one I want to show you. So what you observe here is the CDF of your chances of going to college as a function of the observed mechanical ability, right? Observe, this is the test score. As you see, those who go to college are a little bit to the right compared to those not going to college. That's with the test score. But once you do the ability measure, you see that the impact is the other way around. So the test score is actually the sign that you will infer from using the test score as your independent variable when explaining schooling decisions will be the opposite of the one you observe once you take into account measurement error and family background characteristics. How big of an impact? So as you increase 1 standard deviation of mechanical ability, your chances of going to college are going down in 0.09 log points. That's significant, and with cognitive is positive, that's something we know. Socio-emotional is positive, something we have seen before. But again, if we think about abilities from multidimensional, you would expect different abilities to have different impacts. And we have been living in this world in which cognitive and socio-emotional have both effects are in the same direction, but that doesn't need to be the case. That's one example in which you find this ability having a differential impact compared to the conventional taxonomy. What about the impact on earnings? This is wages, I'm sorry, hourly wages. Positive return on the high school sector wages, but the impact on mechanical ability is larger there. The return on mechanical on the college sector is negative, but it's actually interesting. But that's being explained because they actually have to work longer hours to get the same income level. So it's actually coming from the other margin. Bottom line, the returns are high. They're positive for mechanical ability on the high school sector. That will explain why people with higher mechanical ability levels are not sorting into college. It's perfectly rational from this perspective. They have just different skills levels. All right. Let me tell you a little bit about bullying, because this is something we are trying to figure out. We have been working on this for a while. We're trying to figure out if we can use these factor models to explain this social interaction. With Miguel Urzua, we're analyzing this data from South Korea. Bullying is it's a really important problem, of course. And so what we do in this paper is try to understand that social interaction, that social problem is a function of unobserved dimensions, cognitive again and non-cognitive, using data from Korea. So what do we find? Well, first of all, bullying affects your chances of reporting depression, feeling sick, mental health issues, stressed, and so on. But non-cognitive skills reduce the chance of being bullied during high school. So there you have a chance of a policy intervention, right? Maybe if you can improve non-cognitive skills, you can, in principle, help these kids to deal with this social behavior. So let me show you what we do. This is data from South Korea. As I said, a Roy model, 2 factors, bullying, and different outcomes. Again, factor structure, right? So we have bullying. It's going to be a function of my classmate characteristics and my unobserved components, right? Cognitive and non-cognitive. We have different outcomes, including life satisfaction, some depression scale, sickness, smoking, mental health, and so on. So if I receive bullying, if I am a victim at age 15, I will look at the outcome of that event, the impact of that event later on this dimension. So if I was treated, if I was a victim of bullying, I will receive an outcome Y1. If I was not a victim, my outcome would be Y0, and then we identify these unobserved components using these test scores before the bullying happened. All right. So first of all, again, we have locus of control, responsibility, and self-esteem pre-bullying, right? As a measurement system, factors explain a significant fraction of the variance. But these measures, again, are really noisy, so you don't want to just control for them, use them as a right-hand side variable. What is the impact of your chance of being a victim as a function of your unobserved skill dimensions? What is interesting about this is a South Korean case. It's all about non-cognitive. So if you have high levels of non-cognitive ability pre-bullying, right, your chances of receiving the treatment of being bullied are affected, are reduced significantly at age 15. And then what we can do is we can look at the impact of this these 2 unobserved components. By the way, it's not cognitive. At least in Korea, the effect of cognitive ability does not trigger in bullying, right? It's all about non-cognitive, all right, which is sort of interesting. What is the impact of these 2 dimensions on depression? Well, high levels of non-cognitive ability reduce your depression in both states. Cognitive ability increase your levels of depression If you did not receive bullying, the impact on in the event of receiving bullying, it's non-significant. You see similar effects on some of the other dimensions, but let me just go into what we do at the end. It's about treatment effects, right? I want to see the impact of bullying on these outcomes, right? And what we are able to do is to show, first of all, when you look at stress levels, the average treatment effect of bullying on stress overall is positive and significant. And we don't find evidence on the smoking. And I just want to point out that because there is a lot of heterogeneity, you want to be careful again playing with these factor models because you can uncover some effects. It's actually, if you look at the impact of non-cognitive and cognitive skills on the average treatment effect of smoking, even though the effect on average is 0, you see large heterogeneity as a function of these two unobserved components. So these factors do matter when it comes to understanding how this bullying is affecting different outcomes. I'm not going to get into the dynamic treatment effect, but you see where this is going, right? So once you set it up, once you see how you can use these factor models to link these unobserved components to test scores and decisions and outcomes, you see how you can use them to look at treatment effects and to evaluate policy interventions and to inform policymaking of things that you can do in the context of these models. Factors models are powerful tools. Right? In economics, we have been using them more and more because we have better data, we have better techniques, we have more computational power, we can estimate these factors, and unfortunately, people have been incorporating these test scores into large surveys, and we can use now administrative data to identify these factors and to look at things like this. So, thanks a lot.
Thank you, Sergio. Now, Irini Moustaki, who is Professor of Statistics at the London School of Economics, will give us their comments on these 3 papers.
Okay, thank you, Marco. So I would like to thank Marco and William for actually inviting me to be part of this symposium, which is actually quite interesting. And I've been asked to comment on the last 2 papers that we heard. So I'll try to do it. It was quite interesting to read both of them. I wasn't aware, actually, especially of the second paper. I know a little bit about the first one, so let's see what I have to say and if it is actually interesting or it will make a contribution. So, do I change the slides myself? Okay, sorry. Yeah. Okay. So I cannot see them, so I need to actually be here. Right, sorry. I don't know why it's difficult for me. It was fine for everybody else. So the first actually paper deals with the issue that we kind of discussed in the first session as well, which is about using factor scores to predict an outcome, which I will call here a distal outcome. And so the framework is not having actually covariates affecting the latent variable, but having the latent variable affecting some other variable. And what they try to do is they try to do it in what I will call a one-step approach, because there have been actually approaches that they are not one step, but they're 2 steps or 3-step approaches. So it is now quite known that if you try to get scores and just do your regression independently, that will induce some bias. And it has been known actually for many, many years. And the first, I think, paper that I read in that subject was in 2004 by Bolk and Kroon and Hageners, where they looked into this kind of issue for association models and latent class models, and they published actually an approach in political analysis. So they actually kind of discussed the issue and tried to correct the estimates for bias. So So the model that was proposed by Lynne was actually, let's try to do everything in one go, which is actually the main approach if you do structural equation modeling. So if you do structural equation modeling, you don't really separate the steps. You fit the measurement part of the model and the structural part of the model together. But in structural equation modeling, it's probably not so common to have the latent variable predicting a distal outcome. Because when you do that, what it actually implies is that you're having a measurement model, and at the same time you use your latent variable to explain now another covariate, another variable, which has been used also to measure this latent variable. So the problem also becomes a little bit tricky, because I think when you have a latent variable affecting a distal outcome, which could be, of course, from a practical point of view, from a substantive problem, a very interesting question to resolve. Somehow it is complicated because this distal outcome has the same position as all your indicators that are being used to measure the latent variable. So you have a measurement model and you have another regression that you're trying to do, which doesn't look very different from your measurement model. So if we actually look at the specification here, which would have been if you were doing structural equation modeling, that's what you would have done. But then in SEM, you usually analyze the covariance matrix and you write different equations instead of density functions. So one comment that I actually have here, which of course is all correct, is I don't really see why you probably need to condition theta on z, so the conditioning model. So the measurement model is the, so if you look my second equation there, here, so this is actually the measurement model, and you can see the measurement model doesn't depend on any covariates because you assume equivalence. And then you have the structural part of the model where you actually, that's the regression of interest. So whether actually the theta and covariate z affect a distal outcome y. And then you have the theta that depends on z, and I would actually be interested in that if I was probably interested in a kind of a mediation effect. So that say that z has a direct effect on y, but also has a mediating effect through the latent variable. But why I need to actually condition on that is something that I'm not actually very convinced. What I actually know is that if I misspecify the distribution of the latent variable, will be problematic in estimating the rest of my parameters. So for many years, we believed that whatever distribution we assume for the latent variable makes really not much difference. But I think now we know that, if we have very skewed distributions for the latent variable, so if the population with respect to theta is very skewed or is bimodal, then that will affect, the parameter estimates you get. So from that point of view, I do think, paying attention to what distribution you're going to be using for theta is important, but actually call this a conditioning model and using the same z's that you use there, I'm not 100% convinced that this is kind of necessary, but, I might be wrong about that. So now, so this, of course, approach is very nice because, you don't have to worry about getting factor scores and doing your regression and correcting for the bias because you can do everything in one go. And as long as there is software that can do that, or you can easily estimate it, for example, in a Bayesian framework using JAGs or bugs, then, it will be really ideal, I think, but of course, that requires that you have the item level data, that they are available, in many cases. But then the applied person has to do two things, has to think about the measurement model and then also incorporate the substantive model. And, okay, so let me move to the next one. So then what I would like to say is just to discuss some of the literature approaches that have already been there, mostly for latent class models, so when the latent variable is not continuous, but it's actually discrete. But I think, we can borrow ideas from that literature when it comes to the factor analysis type models. So, for example, there are approaches like one-step approach, which I will call Lynne's approach to be a one-step approach because you do everything in one go. But there are also various stepwise approaches. And I mentioned the paper by Ball, Kroon, and Hageners when actually they used some kind of correction for bias when they were doing it in 2 steps. And there are also 3-step approaches that they use kind of maximum likelihood framework. But the 3-step approach is mainly for the latent class. So what actually they try to do, so let me just give you an idea of what all these approaches are. So the one-step approach is, yes, do everything in one go, as the model we just saw. And so then you can get all your parameter estimates without having to worry to take into account the sampling variability of your estimates or any other measurement error. But the thing here is now that your y variable, so your distal outcome that you're interested in to regression your covariate, is included in the measurement model together with your x variables, that they measure the latent variables. If you look at the two-step approach, which has been actually proposed very recently by PIAAC, who is actually in the audience, and Susan actually works for OECD, so you have all the human capital here to develop this method, is that so here, what they propose to do is to separate the two estimations. So fit your measurement model first. So use your x variables to measure your latent variables. So separate this process from estimating the regression of the distal outcome on your latent variable. But then we know that if you do that, this is going to create bias. So what they do, what they do in the second step is they fix the measurement model and only estimate the regression path of interest between the distal outcome, the latent variables, and other covariates. And they compute correct standard errors. So they correct actually the standard errors to take into account this two-step approach. And the nice thing about this is that they can actually do it in standard software. Yeah? So I think this kind of idea could be used also for IRT models. So if you fit the measurement model first, you fix it, and then you estimate the remaining of the model having the measurement model being fixed. But then you need to do some kind of correction in your standard errors. And so they have this paper that published in Psychometrica. So the three-step approach, it does something slightly different, but again separates the measurement model from the rest. So within the latent class, you get your measurement model, so your latent class model will be estimated only by your indicators, and then they calculate, then you get, of course, posterior means for the factor solution. You get posterior probabilities of being in a particular class for the latent class model. And then what they compute is misclassification probabilities. So, of course, when you're classified to a particular class based on posterior probabilities, there's always a misclassification error attached to it. So therefore, when they go to the step three, they use a maximum likelihood approach where they write down the likelihood weighted by these misclassification probabilities. So you can see there is one step where you do everything in one go, three-step, and now there is also a two-step, which actually seems quite reasonable. Now, what are the advantages of the one-step approach? Is you can do everything in one go. It allows for flexible model structures. You can have nonlinear models in your separate regression. You can combine it with any type of indicators. Lynne mentioned actually that it is robust when the IRT model is misspecified, but other misspecification of interest will be, for example, when you have conditional dependence. So what happens when your distal outcome is actually not independent with the rest of the indicators given the latent variable? So that's quite an interesting, problem or something that might happen. Or you misspecify the distribution of the distal outcome given your latent variable. Now, when it comes to the one-step approach, I think the disadvantages, in my view, is that you mix together the measurement model with the distal outcome regression. And you might want to separate those two. Of course, this is the data-generating model you assume. So the data-generating model you assume is the one where the distal outcome together with the indicators are explained by theta. So if all the model assumptions are correct, then whatever you do the one-step approach, or you actually separate them, you will get the same answer, if the model assumptions are correct. So I think this is, in my view, one of the disadvantages, and Vermont actually has pointed out also, is that every time you add a covariate, you have, or a different distal outcome, you have to re-estimate the whole model, including the measurement model. And by doing that, you, of course, might change the measurement model. So when you add covariates or distal outcomes, the measurement model might eventually change. So you might, for example, need more classes to explain the associations among your indicators. So when it comes to some literature results, so that you know what is actually people have found, is that the performance of the one and the three-step approaches are very similar. Okay, especially, you know, when the model assumptions are correct. So if you have, for example, the sample size is large and you have quite a class separation because most of the studies are for latent class models, everything is actually good. All methods perform well, and you have small bias and correct standard errors and good coverage. They also found that if you have violations, for example, of normality of your distal outcome, given your latent variable, or you have violation of conditional independence, then, of course, things do not look as good anymore. But they found, that, for example, that the three-step approach is less sensitive than the one-step approach. So yes, so I don't really want to say more about it. I just wanted to just let you know that this is actually a problem which has been studied quite thoroughly, I think, in the latent class framework, and could be, you know, also a lot of those results transferred to the IRT or factor models with continuous variables, and especially the two-step approach, I think, because it would be easy to implement. Yeah. So some other recent extensions, so that I also mentioned my name, is that, you know, I was very actually happy to read the paper because recently with one of my PhD students and my colleague, Fiona Steele, we looked into this problem and we started from a very kind of applied perspective, because we had actually a data set that we wanted to have multiple distal outcomes, and then we had also multiple latent classes. So we wanted actually to see what happens if you don't just have one latent variable or one you know, latent class, but you have multiple latent variables with multiple dimensions. And we found very similar results with what they found for the case when you have just one latent variable. So I think those are my comments with respect to the first paper, and I don't have as many comments about the second paper. So I very much enjoyed reading the slides of the second presentation, but I have to say I wasn't able to follow all the details. Where are the speakers here? So what actually the second speaker was trying to do is to introduce latent variables in the ROI model, which apparently is a well-known self-selection model of outcomes, and compute these average total effects and total treatment effects given latent variables. There were 3 very interesting applications. And I ended up with a lot of questions when I was actually reading the slides, because it wasn't very clear to me. So obviously, the ROI model falls within this kind of counterfactual framework. So what wasn't very clear to me is how those actually counterfactuals are being measured. But I think in his presentation, through the second example, I kind of figured out how, by looking at the different ages, this is possible, but I'm not 100% sure. The other thing I wasn't very sure is that how you actually measure those latent variables. So I didn't really see at all the measurement models. I saw the equations of these 2 counterfactuals as the functions of latent variables, but I'm not sure how the measurement model is incorporated there, and when there were the 2 graphs with the estimated abilities and the observed ones, how the estimated abilities were actually computed. Also, you know, since it falls within this counterfactual framework, there wasn't any discussion, which probably is there, about the sequential ignorability assumption that is required to get these causal effects. So I think it's very promising that you know, this is a model that is used in economics, and now covariates have been actually replaced by also some latent variables. But I would have liked to see how the whole model actually comes together and how it's possible to estimate it. Also, I mean, you know, the speaker mentioned the idea of having more flexible latent variables, which is very legitimate. And as I said before, now we know that the distribution of the latent variable could be influential and used actually mixtures of normals that one can do also within standard software by using this kind of hybrid models that Matthias has also worked, where you use latent class models and IRT models to specify, so you use the combination of continuous latent variables nested within latent classes to allow for these mixtures of distributions. But my question is, how can you justify the fact that you need those mixtures of normals, and is there any way to actually look at model selection or model fit in this kind of framework that the speaker used? And I know there is in the example where he gave the average treatment effect and total treatment effect, but I would like to see how this is computed when there are actually latent variables. So those are mainly more questions actually that I had while I was reading it. It seemed very promising, but I wasn't able to capture the whole idea. So I think those are my comments.
Thank you.